that's what I've been working on, and this has been a process. I started typing this out in Canvas, and I got wordier with it than what I intended to begin with, but anyway, it's to your benefit, so I don't think that you're going to mind too much. You know, whenever I do spines and, you know, if I do bony thorax or whatever, it might not be this quite as wordy. But anyway, I started this Wednesday. I started typing it all out. I got about as far as what this is, and I tried to post a picture in it, and everything went away. So I had to start all over again yesterday. So because I started on Wednesday kind of being wordy with it, I felt obligated to go back in and kind of try to reconstruct what I did on Wednesday rather than just bulletize everything. So what I did was I got through knee and left off the femur and hip, and did not get in chapter 8 yet, but I'll get that, you know. So what I did was I made the sections chapter 7, went in toes and feet, you know, kind of kept similar things similar, and went through, you know, some just general information to know in anatomy. I got to finish that thought out. Common fractures include. So, you know, I type the same way I lecture. You know, I start off with one thing, and then something else pops into my mind, and I go do something else, and you know, so you wind up with this kind of stuff. So, anyway, I'll try to remember to finish that thought. But you know, common fractures of the toes are really mainly, you know, obviously broken toes for kicking stuff, and then some in the metatarsals. I think that I included in the ankle one of the more common metatarsal fractures, what we refer to as a Bennett's fracture, and it occurs in a lot of cases whenever you twist your ankle. It's a fracture of the proximal fifth metatarsal. So, you know, if you read through the book, it describes the Bennett fracture being diagnosed quite often on a lateral ankle. Okay, so that just means that you need to open up the collimation enough on your lateral ankle to include the base of the fifth metatarsal routinely. So anyway, did basic information and anatomy, and then went through the projections. Remember, please remember not to study everything, just the things that we cover in here, cover in a lab manual or in this, because there's a lot of stuff. You know, we're not going to do a specialized view of the sesamoid bones or anything like that. So just stick to what's listed, what we cover, what Mindy or Goldie cover, what's in the lab manual, those things. So special projections you're going to go through next semester. So I did also the colors did not translate, it looks like, but I put you know, some things in red that are must know information. I don't mean for the test, I mean for clinical practice. You know, like for example, leg fractures are highly unstable in a lot of cases. So, you know, you have a patient who's got a leg, you know, an obviously broken leg, and you're going to know that the leg is broken because the knee is straight in like an AP type presentation, with the kneecap pointing straight up, but the foot's pointing in one direction or the other. Obvious problem there, right? So, you know, your textbook positioning is not going to apply to that patient. So in that case, what you would be, you know, actually imaging is not what the book describes, you know, with the foot sticking straight up and the femoral condyles parallel to the image receptor. What you would be actually imaging is an AP of the knee with the lateral of the foot. And then you may have to shoot cross table in order to get the lateral in that case. So those are the things that are kind of in red, and I'll go back in and color code those. So there's some of that in the calcaneus as well. Well, not so much calcaneus, but the knee, particularly the patella. So anyway, you've got all that, you've got projections, and understand that this is not the only thing that's going to be on the test. You need to, I mean, it starts off with, well, the original one did. It you know, started off with make sure you know central ray location, structure shown, the basic things. These are the projections with a little bit of color commentary added to it to, you know, to make sure that you know the specific things to focus on, you know, especially in clinicals, and commonly asked questions that I've seen in like registry review books and things like that. So you're going to be tested over the whole thing, but make sure that you know that you read through this as well. So this is kind of a review for lower extremity positioning. I'll try to finish this out before lecture, not Monday, but the following week, so that you'll have it before we lecture over that. But we're not going to get past all this. So you may see some things like PA axial with a question mark, and if you had your Merrills, I'd have you turn to the page where the Honblad method is demonstrated, and there's no angulation on central ray. So axial, not really, you know. Anyway, you'll see some commentary through that. So you've got that. We'll finish up today. The things that we need to talk about today are wave-particle duality and what that means for us, and how different types of electromagnetic radiation behave in different ways and resemble more one than the other. We'll look at inverse square law again and talk a little bit about some other things regarding the inverse square law. Rather than just the intensity, we'll talk about, you know, more radiation protection, and certainly when you apply the inverse square law and how that relates to imaging. We'll talk about the Planck's constant and what that means. We'll talk, you know, we've already really discussed matter and energy, so we're not going to spend a whole lot of time in that. You'll see on page 66 pair production. Pair production is a radiation therapy level of radiation exposure, so you'll get that next semester, so we're really not going to talk about that. So once we get into the lectures, we're looking at maybe about 15 minutes worth of lecture, so short class today. I'm sure that breaks your heart, right? And I told y'all that I was going to try to find a video over the wave-particle duality, and every year I come back to the same video, and it's the reason I do is because it's pretty simplistic, and that's as deep as you need to go with it. You know, all the other ones that I watched, and I watched a few of them, just try to find one that wasn't a cartoon, right? And the problem is that it gets overly technical in each one of those, and this video is short. It's 5 minutes long. So, and that's as deep as you need to go with it. It's not, for our purposes, it does not need to be that complicated. You don't really need to understand the specifics of why and the history of the experiment. I'll give you my history with the experiment, but anyway, if you want more in-depth conversations about it, it's all over the place in here. So that's what we're going to start with, and to preface it, I'm just going to say that electromagnetic radiation, you know, it has a couple of properties that kind of intermingle, right? So wave-particle duality means that sometimes electromagnetic radiation behaves like a wave, and sometimes it behaves like a particle, like a single quantum, like what we open a chapter with. A single quantity, a bundle of energy, a discrete bundle of energy. So all electromagnetic radiation behave in both of those ways, but certain energy levels behave more like one and others behave more like the other. In other words, some electromagnetic radiation behaves more like a particle, and some behave more like pure waves of energy. So what is it? Is it a particle? Is it energy? And the answer is yes. So it's a little of both, right? So we're going to watch this thing, and this talks about electrons, but what we're talking about is, as the wave particle duality of electrons, but what we're talking about is electromagnetic radiation, right? So electrons, every time you hear electrons, just replace that mentally with photons, which is a quantum of electromagnetic radiation, right? So let me see if I can, I never can get just these front ones off. So that, we're gonna take a 5-minute nap. So again, I apologize, it's pretty basic and kind of it is cartoon, really, but it gets us as deep as what we need to know.
What they taught us at school isn't really the way it is, and that our senses are playing tricks on us. You just gotta wonder.
Can everybody hear that okay? Can you hear that okay in the back?
We find ourselves in. Quantum physics says it's all just waves of information. Do I believe that? I hope so. Yeah! And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines. Where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a screen through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. We get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. Physicists were completely baffled by this. So they decided to peek and see which slit actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. It was here that physicists stepped forever into the strange netherworld of quantum events. What does matter? Bubbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
So, a few things with that. Some of the, or one of the videos I was watching was saying that same thing theoretically would happen regardless of what you shot through the slits. Human beings, these things happen, you know, and they followed that up with magnetic ones. They followed that up with the slit would have to be, you know, they said the number, but it was tiny. It was tiny. And they said a human being, you know, could die their whole life and couldn't fit through that slit. And the dark side of me said, well, if you throw them hard enough. So anyway, it would appear that everything has a wave-particle duality. And you can see some of what he was talking about in a swimming pool, right? So if you get in a swimming pool, it's probably going to be a while before you want to do that. But you get in a swimming pool, I don't even know that I don't need the board. I'm just destroying nursing lives here. But you get in a swimming pool and, you know, you pat the water and what do you see? Waves, right. You pat the water with both hands and you'll see that disturbance pattern that he was talking about. But where I saw this was, oddly enough, in a lecture, in a lecture over philosophy. And a guy had an argon laser and he had a lab slide that he completely blacked out. So the thing, no light got through this thing. And he blacked it out. I don't remember exactly how he set this thing up, to be honest with you. But at any rate, he had slides that were completely blacked out, no light could get through them. And then he had other slides where he had adjustable slits. And, you know, he took the argon laser and this you know, he lit it. It was actually a strikeable thing. And he shined it on the slit, and the slits, you know, you got the disturbance pattern. First, he started with the first, you know, with a single slit. And he got the pattern that you saw in the video. And then he introduced a second slit, and you got the disturbance pattern. But if he spread them out far enough, but they were still within the light field of the argon laser, it went back to a single, you know, not a disturbance pattern, but two single lines. So it's weird. It's very strange. And, you know, do you need to know all of that stuff? And the answer is no. It's really just for your understanding of what it is Bushong is talking about with the, you know, the dual nature of electromagnetic radiation being particle and wave. What you need to know is that visible light behaves most like a wave, okay? And X-rays behave most like a particle. So we've got a measurable amount of X-rays, and they behave more like individual bundles of energy rather than a wave. So individual little pieces of energy, truly a photon or quantum, as opposed to visible light acts more like a wave. So that's all really fundamentally that you need to know about the wave-particle duality. Is the higher the energy, the more it behaves like a particle. The lower the energy, starting at the at visible light and going to the bottom of the electromagnetic spectrum, behaves more like a wave. Okay. So, you can, again, dig into that as deep as you want to. We're not even gonna have a philosophical discussion about it in class. That's all you need to know. All right, so we talked about what we could do with visible light and with x-rays, and what were the things that we could do with visible light. We can see, right? We can see because it, you know, but why can we see? It transmits, right? So it's got to transmit through air, through glass. It's got to go through something, right? So you got to have some sort of transmission. So transmit. What else?
Attenuation.
Attenuation. Attenuation is filtration, which is selective absorption. Exactly. Those are the words you're going to be looking for attenuation is selective absorption. That applies to x-rays as well. You attenuate whenever the beam goes through you or your patient or whatever, you attenuate the beam. You absorb more in bones than what you do in air, selective absorption. You attenuate the x-ray beam. The higher the energy, the less attenuation. What determines the energy? KVP, right. So to tie KVP into energy and frequency and wavelength and all that, the higher the KVP, the higher the energy, the shorter the higher the frequency, the shorter the wavelength. All right, so the KVP determines that wavelength. So we've got attenuation, we've got transmission, what else?
Refraction.
Refraction, right. So it enters a medium and it changes speed, and we've got refraction. What else? Reflection. What's the opposite of transmission? Absorption, right. So all that stuff you can do with visible light. What can you do with x-rays? It's a whole lot easier. Attenuate, absorb, or transmit. So it's just those three things, right? So x-ray beam goes through something and it attenuates. And you know, here's the kicker, is that anything it passes through, it attenuates. If there's an atom that can be hit by the x-ray beam, it's going to attenuate it. So where are atoms? Everywhere, right? So does that mean that, you know, that if I've got this air gap that's between here and that back wall, that I'm not going to have any x-rays by the time the x-ray beam gets to that back wall? The answer is no. And the reason for that is because those atoms are there, but they're so spread out, and you know, they're gaseous atoms. They're not doing just a whole lot. You may lose some energy by the time it gets back there, but it's you know, and I proved this one time. All right, so this is my first year as clinical instructor, and you know, they were going through KVP and mass and exposure and radiation safety. And my first year as clinical instructor, and I spent about half of my career at that point in surgery. And when you go to surgery, you're going to notice that nothing that we do here translates to surgery. Not a thing. We're not shooting for diagnosis for a radiologist. We're shooting for the doctor in front of us, right? Whatever he says he needs or she says she needs, that's what we give them. Weird stuff that we do. And then you get into recovery room, and you may have to do some x-rays on patients who've had like total hip and total knee replacements. But the thing is, the recovery room's a great big place, right? It's a great big place with a whole lot of beds, and it's just an open bay in most hospitals. There may be a wall, but it's not going to be a protected wall. It's not going to be a leaded wall. So you make an exposure and people are going to get exposed. And I had a student that was really, really concerned because this particular recovery room didn't even have walls. It was just one big bay room. And they did a cross-table lateral knee, and there was patients on the other side of them. I said, well, how close were they? They said, about 10 feet. I said, the x-ray beam never got there. Never got there. Never even got there. The patient got 0. And he said, well, that's not what Nancy said. I said, I'm going to prove Nancy wrong. So we have one room at what is now UT Maine. I don't know if it's still this way, but room 4, is it still massive compared to all the other x-ray rooms? UT Maine? Anybody? Yes. Six, yeah, not 4, 6. Room 6 is where they used to probably still do sterile procedures, right? So if you look at the ceiling, if it's still the same way, what you'll notice is that there's a, you got ceiling tiles, and then there's a divide right in the middle of it. That used to be 2 tiny rooms, and they made one great big x-ray room, and it's about the same size as this, which is massive for an x-ray room, right? So I decided I was going to prove Nancy and the the textbook Bushong's wrong. I'm right. Yeah. So I took portable in there, and I went 40 inches. I took a film and I put a marker on the film, and I said, watch what happens as I increase my distance. I'm going to increase my distance. I'm going to use as I increase my distance because of we're getting into this here, the inverse square law. See, this is applicable on a couple of different levels. Inverse square law, right? Because of the inverse square law, as I increase my distance, I'm going to have to apply the direct square law and adjust my intensity, which is mass. Right, so I started off 40 inches, set a technique, shot it at 40 inches, backed up. Let's say my technique was maybe 2 mass. Kept the KVP the same because my point was, at the KVP level that we're using, that 10 feet, the patient's not getting any x-rays because the power of the x-ray beam is going to diminish, right? So 40 inches, shot maybe 60 KVP at 2 mass. I was just shooting a marker on a film. So I backed up to 80 inches. What's my new mass? It was 2. Now it's 2 squared is 4. So I go to 4 mass, right? And then I backed up, doubled that. So I'm at 80 inches, I go to 160 inches, right? So what's that, 15 feet? So now I'm in that range. The patient's not going to get any dose. So what's my new mass? 4 squared is 16. So I shot 16 mass. Guess what I got? Image that looked almost identical, pretty much identical to the one I shot at 40 inches. Okay, I just didn't have enough room. So now I go from 160 inches, right? That's where we were. 160 inches to, that would be 320 inches. So now I'm at 30 feet, right? 32 feet. I made the exposure, and so I had 16 mass. So what's my new mass? Now you really got to do math. 64, right? So I'm at 64 mass, and the image looks the same. So guess what I did not do? Prove Nancy or Bushong wrong, right? But was the patient getting a lot of radiation? I mean, they were getting radiation, and that's bad. So, we needed to shield the patient somehow or another. But how much radiation was the patient getting? Not very much, not a whole lot. Why? Well, we got 2 things going on with the inverse square law. I've got I got all my toys up in 215.
But if you're trying to say that if you x-ray patient here and the patient next to you is not going to get any, why would you increase the mass if you're trying to prove it wrong? Because you're not going to increase the mass for that.
Yeah, no, you're right. My point was not that I would increase the mass to protect the other patient. My point I thought I was trying to make was that that patient wasn't getting anything because the x-ray beam, the air was going to magically filter out the x-ray beam. And that doesn't happen. All right. So let's say we make an exposure. I wish I had a flashlight better than this one. But let's say we're going to make an exposure and our field is that big. Okay. So what is that going to cover on me, relatively speaking? Chest, maybe, right? I'll get a chest x-ray. So let's imagine that's at 40 inches, right? So let's say I back up to 72 inches. I still got to have light to make this work. Let's say I back up to 72 inches. Now what am I looking at exposing?
Whole body.
The whole body, right? So you have two things going on here. Whenever you change your distance, you know, you've got, if you don't collimate, then you're still exposing the patient to all those photons, right? So what you should do is, if you increase your distance, is to collimate, beam restrict back down to just the size of the anatomy itself, right? So if you just increase your distance, patient dose, instead of being concentrated in the area that you need it to be, you know, concentrated on, as you back up the distance, the dose to that area is going to decrease, but the overall body dose is going to skyrocket, right? So you got to do both things. You can't just increase your distance. And if you increase your distance, again, what law do we have to use to compensate for our technique? Direct square law, right? So let's say you increase your distance, you don't collimate, you increase your distance, you don't collimate, and you apply the direct square law. Now what's the patient dose? How much are you going to change if you go from 40 to 80 inches? It's a double the distance, it's a factor of 4.
Square. It's square.
Yeah, right? So it's a factor of 4. So you don't call it, you increase your distance by a factor of 2. It's inverse square law, right? So distance change was a factor of 2. So your technical, or let's take it one step at a time, your exposure to the patient is going to decrease by a factor of 2. That's the inverse square law, right? So you've dropped your technique essentially by a factor of 4. So in order to fix that, you need to apply the direct square law, which means you need to increase your mass by a factor of 4, right? But what if you didn't collimate? Now what's your patient dose? So overall patient dose, overall body patient dose, it increased by a factor of 4, right? So moral of the story is, if you increase your SID because of the divergence of the central ray, you're going to cover more of the patient. So it's imperative that if you change from 40 to 72 inches, you increase your collimation. You bring it back down to the same region that you were originally going to expose. Otherwise, you're just going to increase patient dose. Patient dose is going to go through the roof if you don't. Okay?
So if you leave the mass in KDP the same and you shoot just a chest x-ray area and they say they get a total amount of radiation of whatever, and you double your distance but you don't collimate, but you increase your mass, they're getting a overall a lot more dose total?
Yeah.
Okay.
Yeah. So you have to collimate, otherwise you
even though there's going to be like portions that are not getting hit, just
Yeah.
since the whole body's going to absorb those low energy x-rays, since there'll be more.
Well, they're going to absorb high energy x-rays, low energy,
Yeah.
everything. Yeah. So yeah, and you're right. A lot of that's going to be out here, but you know, if you're shooting chest x-ray, how much eye dose are you getting? Maybe off scatter radiation very little, but if you back up to 72 inches and your field increases, because okay. So the reason that the inverse square law works is because, let's say, this would have been helpful if I'd have had one of my flashlights, because I've got some that cast square beams. So let's say you're at 40 inches here. So you back up to 80 inches, and what happens is you're going to have a tendency to think, well, it doubles the size here, but it doesn't. What it actually does is it doubles in 2 dimensions. So that is a factor of 1, 2, 3, 4, right? So let's say your chest x-ray was here in the original, and now it's here in the new one. It looks more like a heart, but it's there in the new one. You're getting blasted eye dose. I'm not drawing this, but you're getting blasted. Yeah, everywhere, right? So you have to collimate, otherwise your patient dose goes. Even though some are going to completely miss the patient, you get an overall body dose increase. So 2 things. All right, so back to electromagnetic radiation and the things that you can do with X-rays versus visible light. So what do we call things that light will go through? Transparent, right? So what do we call things that attenuate light?
So,
Lenses. Sometimes we use lenses, you know, like sunglass lenses. But it's another word that means partial transmission.
Translucent?
Translucent, right. So if you look at the filters up there, can you see the light bulbs? No. It's a specific type of translucency that lets most of the light through, but it's a diffuser so that the light spreads out more. Okay, so transparent, translucent, and then if you can't see through something at all, that's what we refer to as opaque. All right, so in X-rays, again, what we have is transmission. We have selective absorption, so we have relative translucency, kind of, sort of. And then we've got, you know, something that's opaque, something nothing will get through, right? So we really fundamentally only have two types of tissues that X-rays interact with. It's either going to completely block the X-rays, right? So completely block the X-rays, that's what we refer to as not opaque, but we're going to put a radiopaque. Yeah, if something is radiopaque, that means no X-ray is going to get through it. Okay, so if we have attenuation of the X-ray beam, attenuation is going to be partial absorption, partial transmission, and that's going to be something that is radiolucent, right? So we don't have anything that is radioapparent, right? So we only have two types of things: something that's going to absorb and transmit, you know, a portion of both, and that's going to be radiolucent. And then we're going to have other tissue types that are not really tissue types, but other things that are going to be radiopaque. Lead, radiopaque. Pretty much everything except for heavy metals and very, very thick concrete are going to be at some degree radiolucent. Okay. All right. So any questions on that?
So earlier you said that attenuation was absorbing.
Selective absorption. Yeah. So
Selective.
yeah, partial absorption, partial transmission.
So selective absorption and then absorption are just completely like they're their own categories.
Yeah. Yeah. So absorption, especially in context of radiology, is nothing gets through it.
Okay.
Yeah. So that would be your radiopaque versus your radiolucent. And visible light, you know, you've got varying degrees, you know.
Are the colors and everything going to be on the test?
The wavelength of the colors?
Yeah.
No. No. What's going to be on the test is what is at the upper end of the electromagnetic spectrum, what's going to be at the lower end of the electromagnetic spectrum. I'm not going to ask you where red light is in relationship to yellow and blue, no.
So will we need to know when we use inverse versus direct square law?
Yes, and the short answer is if you're looking at a question that says how much, and this applies now, next semester, all the way through the registry. If you're looking at a question that says your intensity is blank at 40 inches, what is your new intensity at blank, right? So, you know, your intensity is 26 at, let's make it easier, 28 at 40 inches. If you go to 72, well, let's say we'll go to 80 inches. What's your new intensity? And you don't do anything to the technique. You don't read anything into it. It's asking you what your intensity is with the change in distance. You're going to apply the inverse square law, right? Yeah, indirect, inverse, same thing. So your new intensity would be the 28 divided by 4, so your new intensity would be 7. Right. Okay. So what is your, what's your little cheat code for changes from 72 inches, or I'm sorry, 40 inches to 72 inches? How much of a change in intensity are you going to see? And I'm going to finish your question in just a second, which law to apply. 3.24, right? So if you go from 40 to 72 inches, you don't adjust your technique, then your new intensity is going to be whatever your original intensity was divided by 3.24. When's it going to be 3.24? Every single time you go from 40 to 72 inches. If you go from 72 inches to 40 inches, what are you going to do? Well, you decreased your distance, so the inverse of that is to by 3.24. When do you multiply by 3.24? Anytime you decrease from 40 to 72, or from 72 to 40 inches. When?
72 to 40.
How? What frequency? Every time.
Oh.
Every time. Right. So you don't need to work that, right? It's every single time. It works like that every single time. All right. So double 4 times. 40 to 72, 72 to 40, 3.24. The two things that you're going to do, have a tendency to do, is double the distance. Your intensity decreases by 2. And that, every time you do that, the answer is going to be wrong. Yeah. So you increase your distance, 40 to 80 inches. I guess that's 72. 40 to 80 inches, then your intensity is going to decrease by a factor of 4. How often? Every time, right? Every single time. It's not going to be 2. I'm pounding this into you because you're going to make this mistake all the way into your second year. Okay. So now the second half of your question: when do you apply the direct square law? Those questions are going to be when you want to maintain the image receptor exposure. Okay, so the things that you're going to look for the inverse square law is your intensity change with changes in distance, and is usually going to ask you for radiation exposure measured in MR, milligray, something like that. Your direct square law questions are going to be asking you about new mass with changes in distance. Okay, so if it's mass, then you're going to be looking at changing your mass, and that's going to be the direct square law. So if you increase your distance from 40 to 80 inches, because you lose your new intensity is 1/4 what it was before, what's your new mass? 4 times, multiplied by 4. Your intensity dropped by a factor of 4, so you have to increase your intensity using mass by a factor of 4, right? How often? Every time. Every time. Right. So you go from 40 to 72 inches. You got to increase your mass by a factor of 3.24. How often? Every time. If you answer 2, you're wrong. You're going to get it wrong every time. Okay, that's the one thing that you're going to do wrong. The other thing that you're going to do wrong is go in the opposite direction. You're going to apply logically the direct square law when you should have applied the inverse square law, or vice versa, right? So you're gonna select, and you're gonna get both of these answers. So if I ask you a question that says you've got 16 MR at 40 inches, you increase your distance to 80 inches. What's your new intensity? And I'm going to give you increase by a factor of 2, so you're going to lose intensity by a factor of 4, right? So the answer is 4. I'm going to give you 4, but I'm also going to give you, I'm going to give you by a factor of 2, so 8. I'm also going to give you, as if you went in the opposite direction, I'm going to give you 64. Okay? So, you know, watch for those. Okay. Always 4, and that, okay, so I'm not gonna give you changes from 40 to 60 or 40 to 54 or anything like that now, or even next semester. But in your sophomore year, you're gonna have to actually work the inverse square law. All I want you to know right now is 40 and 72. You know, 40 to 72 or double distance, okay? Okay, just focus on those, and you don't even have to work the inverse square law. Just get those locked in, and we'll worry about actually working the inverse square law next year. Okay? Any questions on that?